So first, I would like to thank the organizers, to Max, putting things together, to Norberto, also doing a lot of work here. And he helped me on Friday or Saturday, it was in a crash course with WebEx. And hopefully the benefit is now that it works. And also to Maria for introducing me. Good. So when I was asked to speak here, the idea came up that I speak a little bit about recent work of Michele Elia, who was a good friend of mine who passed away in April 7. And his work was really related to the problem of integer factoring. He was driven to large degree. And so I want to address that a little bit. So let me start I will just explain the problem of integer factorization and just some simple algorithms or trial and error things which exists around. So this will be the first part. And then I show you two main avenues of how integers are factorized in modern time. So the one goes back to Pollard, and it is essentially, it's called Pollard rho, Pollard p-1, and it culminated in an algorithm of Henrik Lenstra using elliptic curves. And it's probably the best algorithm if you have a composite of several prime numbers, and it will catch any prime factor which is not too huge. Now, the other avenue, which is heavily investigated, it really has its starting point in the quadratic sieve. And very early on, people have been using continued fractions to get a factorization method. And this whole set of algorithms culminated in the general number field sieve. And so this is probably the state of the art for the best factorization in practice. So the record of 2009 was a 768-bit number factorization. Now, Michele Elia also was fascinated by continued fraction and came up with a completely kind of independent new idea of factorization. And I will at the end then explain the essence of his three papers, and there is work to come. So here's a picture of Michele, of those of you who have not met him personally. So I did this picture myself when I once visited him in Torino. I found it funny that he resembled, in my opinion, Christopher Columbus. And so Michele, the first time that I met him was probably in a conference around 2000. And then around 2001, he visited me at Notre Dame. I was at the time in the United States professor at Notre Dame University. And since that time, he visited me in Zurich twice a year before.
Joachim?
Is there something?
Sorry for interrupting you, but I think it's nice now that we can see the picture of Michele, if you can also see you. So please, if you can turn on your camera so that we can...
Oh, okay, so let me think actually, if is my camera off? Okay, let me think here.
So that we can see
I have here,
you and your presentation.
Somehow it, let me think. So now it's, actually my camera is on, I believe. Can you see me?
Now.
So it's only if I switch to the full screen, you cannot see it. I think this is probably that I don't share the application. That was some difficulty I have.
Okay, so go on, sorry.
Okay, so please, thank you.
I think, you see, maybe I could try to share the application, but I haven't done that. Let me hear, but then I don't know how to share.
Okay, thank you.
Sorry, so then I do here. So now it's back to the. I think you just see now my screen, and I'm not part of the screen, so. Okay, my camera is on, and in principle, yes. Good. So anyway, in 2001, he visited me the first time, and ever since, he has regularly visited me when I was in Zurich, maybe twice a year. And Michele was a fascinating person. He was very kind and very knowledgeable. And his early work, really, his first degree, doctoral degree, was from Politecnico Torino in 1970. And his early work was really in coding theory. And my engineering colleagues know Michele only from the world of coding theory. But he had always a real passion for mathematics. And in 2001, when he visited me, I realized he said he used to have an even better ability to do arithmetic calculation in the head. I mean, when I'm saying that is take a 2-digit number, raise it to some power modulo, a 4-digit number. He trained that himself, that he could do it. And he was extremely fast in large arithmetic computation. When I then later, in recent years asked him also about this question, he said, oh, he's so slow now, but he was still quick. But anyway, so that was on the mathematical side. He liked also to read old books, the original work of Gauss, of Legendre, of Dirichlet. And he studied what these masters in mathematics, achieved 200 years ago. Last but not least, he always had also a passion to cryptography early on. And some of this work has not been published, so he just, kept it private, or there were private exchanges he had. And so this was fun sometimes to listen to him and to learn what he knew in this area. Now, his work on continued fraction with relation to factorization, grew up. For many years, he just studied it by himself. And it was also 10 years ago, he told me about something he realized is when he did the continued fraction of square root of the natural number he wanted to factorize, then often somehow, if you looked at the period, the middle term essentially was a number. This was a periodic sequence, and so he could identify certain numbers in the sequence, typically the middle one, which the GCD of this number would then catch the factor. And so that fascinated him, and he kept working on it. And in the last 1.5 years, he published 3 papers on this thing. And I thought, I want to tell you a little bit the story and give you the background and the glimpse of it. And even though I am really not a specialist in number theory, and some of his papers on the chunks infrastructure method and so on is quite heavy mathematics, which it involves. But I hope, after my talk, this encourages some of the young researcher to go in his footstep. The third of this series of papers was deposited on arXiv on March 30 this year. And he passed away then on April 7 this year, just a week later. So let me now start with the basics of factorization. And so throughout the talk, we will describe algorithms to factor simply an integer n, which is composite, is p times q, and p and q are 2 prime numbers. So this is in my notation throughout the talk will be this situation. And many of the early algorithms had either exponential runtime or work only for special type of numbers. So this was really the early situation. When I say early, this is probably before 1990. And so, for example, a trial and error method would be try all prime factors up to the square root of n. And so this means the complexity of this algorithm is big O of square root of n. And we call this in number theory an exponential time algorithm because it's exponential in log n. So this is a stupid simple method which works fine if you want to check if 101 is a prime number. You just check if it's 2357 is not divisible, so hence 101 is prime. Now, here is another idea which elaborates, goes a little further. Let's take define M as the floor function of the square root of n. And now compute k equal to m factorial, 1 times, 2 times, etc. m, modulo n. Now it's immediately from simple algebra that this k actually contains the smaller of the factors of p and q and not the other. So if n is p times q, p is smaller than q, then k contains the factor p but not the factor q, and hence a GCD computation of k and n will give you p. Also note that Stirling's formula can approximate m factorial with extremely high accuracy. So there is even work which shows how to approximate better and better this m factorial. And so you would think that would be a cute method, just get an extremely accurate estimate for m factorial, and then maybe if you're a little off, try all possibilities and do the GCD. Well, the computation then would give a non-trivial factor if you have the k. But the problem with this method is that Stirling's formula is highly accurate in the first digits of the expansion of m factorial, but not in the last digits. And if you do the computation modulo n, you really need also the last digits to have it accurate. And hence this method fails. So this is just some trial and error. Now, another thing is, people were trying to get towards polynomial time algorithms. And in 1994, Peter Shor derived an integer factorization algorithm which actually has polynomial running time, but you require hardware, namely a quantum computer, which we don't have. And specifically, he showed that it roughly takes in the order of log n square quantum steps on a quantum computer to do this factorization in polynomial time on a quantum computer. Well, the problem is you need a lot of qubits in this quantum computer, and I think so far what they really can do is factorize the number 35, but of course in polynomial time. So they find 5 times 7 in polynomial time. But this is about the state of the art, but there is on the horizon, of course, a danger that hardware will improve. And for that reason, the crypto community is frantically searching for alternatives to systems which are based on factorizing and systems based on DLP or over an elliptic curve. Now, just for the complexity of the problem of factorization, there was a very surprising result in a related problem. And this is to determine if a particular number is prime or not. It eluded for a long, long time also this problem to have a deterministic polynomial time algorithm to make sure if a number is prime or not. There were things, practically prime numbers are done with probabilistic methods. And under certain very heavy assumptions like generalized Riemann hypothesis, one was able to also have deterministic algorithms, but it eluded it on a Turing machine. And so here came this extremely surprising result nobody expected in 2004 by Agrawal and two of his undergraduate students, and who came up with a polynomial time algorithm if a number is prime. And so the basic idea is based on the following lemma. An integer a, let a be an integer co-prime to n, then n is prime if and only if, so you have kind of this freshman dream, x plus a to the n is equal to x to the n plus a modulo n. Clearly, when n is a prime number, then this statement holds, and it's not hard to show that if n is not a prime number, this statement is wrong. Now, that was the start point of Agrawal and his two students, and essentially what they could show is if n is not prime, one can find in polynomial time natural numbers a and r, so you don't compute x plus a to the n, fully, because this has n terms in general, but rather you make it modulo x to the r minus 1 and modulo n. So you reduce it via two elements, an ideal generated by x to the r minus 1 and n, and they showed that in polynomial time, if n is not prime, you necessarily find a little a, and typically a is just some small numbers, and r is typically, I think, up to 3 you need, and then it's guaranteed that this number is actually not prime. Good, so that if this method works, one could think, could one establish from this a factorization problem? And for this, I give you just here two examples. So let's take n equal to 35. And if you take x plus 1 to the 35, the expansion looks in the following way. Or if you do it with 2, the expansion is given in the second line. And note the following, that the only coefficients which survive, the GCD of these coefficients with 35 always gives a factor. And similarly, the exponents which have non-zero coefficients, the only exponents which there are exponents which are either divisible by 5 or 7. And one immediately can show that this is true in general. And so one could be tempted just to catch any of the factors of this expansion, and you would be done. I tried at some point, and I didn't succeed any further. But it's kind of, I thought it's a cute observation. And if somebody wants to play around, be my guest. Good. Now, so even the knowledge of any of the exponent of any non-zero monomial will do for the factorization problem. Now, a major idea was developed by Pollard. John Pollard is probably really, in the 1980s, 1990s, the dominant person with new ideas in the problem of factorization of integers. And he pushed the whole area quite a bit forward. And his first idea was the polar row method. And I do it here abstractly, is let V of Q be an affine or a projective variety defined by polynomial equations with coefficients in the integers. Now, denote by V of Z modulo NC the rational points, and consider now the decomposition as V of NC as the one divisible by P and the one divisible by Q points. So the Fp rational points and Fq rational points. So this is essentially Chinese remaindering theorem that you have this decomposition. Now, the goal would be to construct a dynamical system. So Pt plus 1, it can be time varying or time invariant. So with, as I wrote it, it's time varying, f of t and p of t. And you start at a point p0. And so the goal is that you construct a dynamical system which has a limit point or at least a small limit cycle. Now, if you can do this, then you immediately, and modulo p, only modulo p. So then by following the coordinates of the pair pt, p2t, so one will find an integer tau, where tau would be the period, you know, of the limit cycle modulo p. So that such that p tau is equal to p2 tau modulo p. And once that is, a simple GCD computation will lead to a factor. Now that might be here kind of an abstract method, but actually this is what he then applied in the polar p-1 thing. But before I say that, I would like just to remark that over the real numbers or over the complex numbers, it's very easy to construct dynamical systems which have one limit point. So for example, if you, over the reals, start with any number and always make half, half, half. So pt plus 1 is 1/2 of the previous. And then obviously that converges to 0. And similarly over the complex numbers. But over a finite field, this is not so obvious how that can be achieved. And at some point I played a little bit around, and so just heuristically, for example, the following dynamical system, if you just do it over the projective line modulo p, so this is xt plus 1 is xt square minus a times xt square. So once this number hits 0, it stays at 0. And if p is not too big, actually everything converges quite fast to 0 if you iterate that thing. And interesting is if you don't take the squares, it will not converge. You know, for example, if you take 3rd degree polynomial or 5th degree, it doesn't work as nicely as with the squaring. It's just also something if people want to play around. There is actually literature on dynamical systems over FP, and it's an active research area, and I haven't followed up the most recent of it, but you find literature on that as well. Now, what was the polar p-1 method? Well, maybe if you were in a crypto class, you have seen that. So the point is, if either one of the two prime factors, either p-1 or q-1 is so-called b-smooth. So this means b is a reasonable small bound. Let's take 1000. And to say b-smooth is that p-1 factorizes with integers all smaller than 1000. So if this is the situation, then one can develop an efficient algorithm for factorization. And I'm presenting it now in this idea of dynamical systems, which is not probably what you see in the literature. So if you have seen it before, you will immediately understand this one. But I think intuitively, this is actually easy to understand as just for the polar p-1 method is, well, actually I wrote here modulo p, you do the dynamical system modulo n, but if you do it modulo p, then this one will converge to 1. So if p-1 is b-smooth. So what you're doing is you start with a point, any point x, and then you raise it to always to some small prime numbers. To the power 2, to the power 3, to the power 5, And you keep going with this until p minus 1 factors your product here of the AT. And obviously, if you do here enough, you know, factors of 2, enough factors of 3, etc., you will achieve it for any p minus 1, which is B smooth. And hence, once you achieve that, then a simple GCD computation of this number with n will reveal you a factor. Now, this is, of course, only works if p minus 1 or q minus 1 is B smooth. And for that reason, cryptographers soon said, okay, we have to use only prime numbers p which are safe primes. And safe primes are that p minus 1 is 2 times another prime number. And then it's as far as possible a way to be B smooth for any bound. And so Pollar's p minus 1 method didn't work in general, but then came Lenstra and said, hey, we can do it over elliptic curves, the same idea with a similar dynamical system, but this time it doesn't matter if p minus 1 is smooth or not, because all what matters is that the elliptic curve over integers modulo p has a smooth order. And since the number of points on an elliptic curve randomly constructed is essentially uniform over the Hasse interval, so what you have is that you can actually randomly start with an elliptic curve where you don't know p and q, but you can look it as an elliptic curve over integers modulo n, which as abelian group you still have this isomorphism coming from the Chinese remaindering theorem, and then like in Polar-Rho, you look at the dynamical system, pt plus 1 is equal to at times pt, where the at are small prime numbers, and you let it run. And it will happen then at some point that either modulo p or modulo q, this dynamical system will reach the 0 point. And at that point, you have again a GCD computation, and you can catch a factor. So Lenstra's elliptic curve factorization method is the most powerful if you have several prime factors and is state of the art. But it really goes back to the method of, what do you want to say, of Polar. Now, another set of ideas is very, very old, and it's based on roots of quadratic equation, of quadratic polynomials. So let Q be a quadratic polynomial with coefficients in integers modulo n. And the lemma is factoring n is polynomially equivalent to finding 3 different roots of this Q of x. Well, on one side is, if you have the factorization, you can compute the roots modulo p, and you can compute the roots modulo q in polynomial time, and then Chinese remaindering will give you all 4 roots. Now, vice versa, if you have 3 different roots, you just take differences and the GCD computation, and you find the factorization. So it's a very easy lemma. Now, constructing a non-trivial solution alpha beta of very simple quadratic equation x squared minus y squared then will give you a 2/3 chance that you actually catch a factor. So non-trivial means alpha is not beta in integers modulo n. And so all these methods here from quadratic sieve, number field sieve, and some methods due to Klaus Schnorr play in finding solutions of this simple quadratic equation. So this is the quadratic sieve is here maybe the easiest and the starting point, and it searches for non-trivial solution alpha beta of x square minus y square inside that ring. Now, a remark is taking a random element alpha and computing alpha square equal to k modulo n and praying that this k is a square is simply not workable, because you can get for k almost anything, and the chance that this is a square number, if n is, a 100-digit number, forget it. So better ideas are needed. And so that was the starting point of the quadratic sieve. And there's one part of it which is actually also already much earlier used continued fractions. And so for this, let B be a factor base consisting of the first t prime number. So P1 equal to 2, P2 equal to 3, up to Pt. And so this is my factor base. And now, so the goal is to find an alpha not such that alpha square modulo is equal to k modulo n, that this number is a square, the k, but rather that k can be factored over the factor base. So we want that k is equal to P1 to the E1, Pt to the Et, and with integers. Now, if K1 and K2 both factor over the factor base, then also K1 times K2 and K1 times K2 inverse, modulo n, you immediately have such a representation. And so in this way, one can solve a linear system of equations to find a beta such that alpha square minus beta square is 0. So I omitted here the details, but for the ones who see it the first time, the goal is essentially the k is a square if all the E1 to Et are even numbers. And since the property, if you have two, also the sum and the difference of the exponents are of this form, you essentially just set up a linear system of equation over the binary with the exponents, and you are looking for a solution which is 0 or even at all times. Good. So now, using ideas going back actually to Legendre and Krejcik, Lehmer, and Powers, it is possible to use continued fraction expansion of the quadratic number an. And the goal here is actually, if you go here back, you just make an alpha square and then is equal to k modulo n, and you're praying that you can factor it over the factor base. It would be really cute if you can, generate k's where k are relatively small, and not, if n has 300 digits, that you are dealing with a 300-digit number which should be factored over the factor base. So being a little smarter, you actually can achieve it that the k is in the range of the square root, so only has 150 digits. And so in order to achieve this, researchers actually used continued fraction, and what they did is, once you have such an irrational quadratic, namely a square root of an, where a is some small number, 2, 3, 4, 5, and you are multiplying this square root, then you can approximate it as fraction p over q, and the continued fraction algorithm essentially gives, in some sense, the best approximate as a rational of an, and then an easy computation shows that p square minus q square an is a number k, and this k is actually in the range of square root of n, actually less than 2 times a times square root of n. And if a is small, this is essentially in the range of square root of n. And in this way, so p square is k modulo n, and if you read this equation modulo n, then you see p square is equal to k modulo n, and the k is small. And now you try to factor the k over the factor base and keep going as I explained it before. Now, this method uses continued fraction, and Michele, in a different way, used continued fraction as well. But let me quick go to the quadratic sieve. They actually, in the quadratic sieve, are not using continued fraction. Due to an idea of polar, they found a clever way, like the sieve of Eratosthenes, to search a large interval of integers and to find all the numbers which are B-smooth, you know, factor over the factor base. And so instead of testing by division, if a number k is B-smooth, a sieving procedure is applied. And so then you have in a very large interval, all the numbers which are candidates to be B-smooth, and this is a fast speed up. And in addition, also in the quadratic sieve, they have a method where it spits out alpha square equal to k, where k is in the range of square root of n. So the quadratic sieve has so-called sub-exponential running time. And in 1988, again, John Pollard developed the special number field sieve, which can be seen as a generalization of the quadratic sieve. And so the special number field sieve, for example, was able to factor some Fermat numbers. And soon thereafter, around 1991, Joe Buhler, together with Henrik Lenstra and Karl Pomeranz, came up with the generalized number field sieve. And this is really, of the general algorithms which are known, the best algorithm. And in 2009, they factored actually RSR 768. So this is a 768-bit number. Good. Now, the rest is, I want to quickly mention some interesting work of Klaus Schnorr, which goes this avenue, and then I concentrate what Michele did. So Klaus Schnorr actually was working on factorizing algorithm for 30 years. He became emeritus like 10 years ago. And one of the basic approaches is actually, in order to achieve the x square minus y square equal to 0, is to look at the following equation, that both on the left, you know, where you had the alpha square, you also look at numbers only of the form p1 to this, and this is prime numbers, and q1 to qt are also small prime numbers. And he looked for relations of this form, and so these are small primes. And now the point is, you can look now at the Diophantine equation where you plug in here times n, this equation here. And if this is approximately the same, using logarithms over the reals, one has an approximate subset sum problem. You know, the exponents become here integer numbers. And so you have x1 times the logarithm of p1 to xs times the logarithm of ps, and you want that this is approximately n. And this subset sum problem then translates over to a lattice problem, and Klaus Schnorr is really the world expert in lattice reduction. And so in 1993, he already wrote some papers on this, and he estimated that a 512-bit number requires a basis reduction of a lattice of dimension 6,000, and where the entries are in the range of 1,500 bits. So at that time, that was out of the range. And but this year, he published also about the date when Michele passed away. He deposited a paper at the ePrint archive of the IACR, where he claimed actually that 800-bit numbers can be factored efficiently with his method. And that would, of course, be quite a feat, and he even says efficiently. The problem was his April paper had some clear mistakes in it, and he retracted the paper. In this July, he posted an updated paper where he claims still the same thing. So this is something, you know, people probably should look at. And the other thing is now Michele's work. So I already mentioned continued fractions. And so a simple continued fraction of some number is a sequence here that you always have 1, and so a0 plus 1 over, and then in the denominator is a1 plus 1 over, blah, 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 and you keep going. And to describe this continued fraction, you just describe it now by the numbers A0, A1, A2, A3, etc. And, you know, if you truncate it, it's always a rational number. And if you do this for any real number, then this rational number is in some sense the best approximate as a rational number of this irrational number. Now, a finite continued fraction whose elements, etc., are integers. So if it's finite, if it stops at A17, of course, this is a rational number. And one can show that every rational number has actually a finite continued fraction. Now, Lagrange showed already the very interesting result that every real irrational root R of a quadratic equation, so this is called so-called a quadratic irrational, so a root of this, that's also a irrational number, so can be represented by an infinite simple continued fraction. And what is very special at this situation is it's actually ultimately periodic. And Lagrange's theorem goes in both directions. So one writes then, you know, here is the pre-period. It starts at the A0, that's the first, and then up to AS. And from here on, it's then periodic with period tau. And Michele realized that if he can catch the period of square root of n of this continued fraction expansion of square root of n, then he knows how to factor it in polynomial time. So R is the, and he says so that that this number R has pre-period S and period tau. So the goal of his whole work was how for a general square root of n can I compute actually the period of tau. Now, Lagrange showed that infinite simple continued fraction of an irrational number is periodic if and only if this number is a quadratic irrational. So that's another Lagrange theorem. You know, of course, the Lagrange theorem on groups. But this is the one which is in number theory extremely important for the work of Michele. Now, Legendre describes a constructive method for computing the representation of a positive square free number n as the sum of two squares. And the method uses also the infinite periodic fraction expansion of square root of n, and it works as soon as the period tau is odd. Now, in the case that the period is even, there Michele found early on that the middle term essentially of this in the period of this continued fraction contains always either the factor p or the factor q. And so this is what he first realized on computer searches by heuristic, and then developed a theory around it. So the theory is now documented in 3 papers. So Elias 2019, 2020, 2021. So the last one in 2021 was really just posted on arXiv on March 30 this year. And a week later, Michele unfortunately passed away much too early. Now, for this, assume and quickly explain the basic idea is let H be the class number and R the regulator of the number field Q adjoint square root of n. The main theorem of Michele states if the product H times R is known exactly, then there is a polynomial time algorithm for factoring n whose complexity is polynomial just log n to the power 4. So the effort should be, can we compute H times R? And so that is essentially the method, the goal, what you have to do. And once H times R is computed, he also shows that one can compute efficiently the period tau of the continued fraction of square root of n. And then he uses something called Shanks infrastructure method and the celebrated theorem of Dirichlet. And this Dirichlet theorem actually gives an expression of h times r as an integral expression where you numerically can evaluate. And then in this way get h times r with great accuracy. And two of my students, a former student is Karaturian, he actually discussed with Michele this method, and in the preparation for this talk we contacted him, and what practically can be done, he thinks, he pointed me to papers, is that one can make efficiently the computation up to about 110-digit number. So this is like 350 bits. This seems to work, and to catch then the exact number of the product HR, and from there then efficiently with log n to the power 4. And this is essentially just baby step, giant step to find the middle term of the series. One catches the factor. And so it will be the question of future research to study the feasibility of the computation of HR more accurately. And as you see, you know, with any improvement, you can actually improve on integer factorization. Probably if you just play around with Maple, and Maple has extremely good algorithms for factorization in it, then Maple starts to choke probably at 300 bits. And so this method, if you combine it together, might even, you know, be better than these methods implemented in Maple. And I think Maple has implemented also the number field sieve, you know, for larger numbers. Good, so this was my overview of this work of Michele, and I just have here maybe the papers I mentioned. So this is the famous paper, Primes is in P, which was published in 2004, then in Annals of Mathematics. So this is a deterministic polynomial time algorithm in log n to the 6 is it actually now. They published to the power 7.5, and then it was improved. And here are these 3 papers of Michele. So 2 of them are preprints. So this is, and one was actually in Seminario Matematico and Politecnico Torino, published last year. And finally, for the ones who are interested in Klaus Schnorr's work, you find the report on EACR ePrint archive.